And welcome to this tutorial on local descriptors and on local feature extraction and learning. So the first thing I should say, of course, is what are those local image descriptors? Well, they are a tool to match things. So what we want to know is, given an image, where do points go in a different image of the same scene taken at a different time. So it can be a pixel, or it can be a region. So we want to be able to say that the region on the left is the same as the region on the right, even though there's been a substantial deformation between the two. And this has been a topic of interest for a few years because it allows you to do a whole bunch of things. So among these things are matching points in images taken from very different viewpoints and do 3D reconstruction, and also perform structure from motion and SLAM. You can also do image-based search, and you can do tracking, which is one of the big applications. The advantage of doing this using these local features is that this tends to be very robust to occlusions. If you lose a few, no big deal. You can still do it. And that's why they are used in things like augmented reality and people detection. Another thing that they've been used quite a bit is to detect objects in crowded scenes for the same reasons, because if you detect a few key points and miss the others, it's okay. You can still detect the object. And on a different theme, we all have cell phones in our pockets that can stitch images, and these typically use key points as well. So they are very useful, and they've been used extensively for the past 15 years. And the basic principle of all these key points, and something we will talk about for the next 3 hours, is that you take an image region, you build a descriptor of a local patch. So the descriptor here is represented by the red, blue, and violet histogram. And what you want is that this histogram, or these feature vectors, are such that if you take the same point or the same region seen under very different perspective, the descriptor will be close. In other words, robust to changes of viewpoints, but also changes of illumination. And at the same time, it's very distinctive, because if two points are different, the feature vectors ought to be different no matter what the viewpoint is. So this has been going on for quite a while. So if we do a little bit of archaeology, we can go back to the late 20th century with some early methods that use derivatives and high-order derivatives. But that sort of started the field, but it didn't work all that well until SIFT. The turning point for this is SIFT, 1999, where so David Lowe came up with this way of finding interest points and of matching them that was very robust, that really worked. And for all of us who have gray hair, I remember we were floored. I mean, for the first time ever, we saw a computer vision algorithm that worked. I mean, now with DeepNet, it's banal, but at the time, it was, wow, it worked. And many of these applications I've shown before started being practical because of that. But things don't stand still, so eventually people worked on improving SIFT. So one of the improvement was to use binary descriptor, and we'll talk about that later in the tutorial, to make it faster and more efficient. Then, of course, around the same time, machine learning became big in computer vision. So SIFT is entirely hand-designed, but it was relatively soon realized that you could perhaps do better if you trained it for specific scenarios. And of course, in recent years, CNN and deep learning have arrived, and the new methods, of course, are deep. So that's actually an important thing, that the second major event, so around 2000, computer vision algorithms started to work. Around 2012, 5 years ago, I mean, deep learning has existed for quite a while, much longer than that, but that's when it really burst onto the scene, and the majority of the field became aware of it. And the question is, does it make everything we've done before completely obsolete? So in particular, if we look at SIFT, so this is the Google page, the Encoder page for SIFT. So it is the most cited paper ever in computer vision. But it's interesting, so the vertical red bar is 2012, when the revolution started. And you can see that the curve looks like it's not growing anymore, it's plateauing. Which makes sense, because people got interested in other things. And there's a number of things that you could only do with SIFT that you can now do with deep networks. So of course, it begs the question, is SIFT dead? And are we all wasting our time today? Because that's really the question. And I don't think so. So it will endure, yes. And why will it? Because there's still a great many things that key points are good for. So when you need accurate geometric estimation, it's nice to have precise locations in images to do things like bond adjustment or SLAM. Key points are good for that. They are very efficient for real-time applications because essentially they allow you to consider only a very small relevant part of the image. They provide an effective way to compress the information in the image. One good thing about non-machine learning algorithm is they don't need to be retrained for every new application. So for applications where you have lots of training data, it's fine to retrain. But for cases where you don't, you want something that works out of the box, a hand-designed method is not so bad. And finally, in fact, what I've presented as kind of an opposition between old SIFT and new deep learning, well, that's not the way it is. What's really happening is a lot of the ideas that were in SIFT and its successors are now being recoded into deep pipelines. So the ideas are simply migrating, which is, I think, a good reason why it still makes sense to try to understand what the original ideas were before putting it in a deep net where you don't understand anything. So probably, I mean, I know I don't have a crystal ball, of course, but I would think that if we meet again in 5 years, we'll be talking about algorithms that combine deep learning and the sort of key point matching that's made possible. So with this in mind, what we are going to talk about is first a bit of archaeology, which is what I'm doing now, the classic features. Then we will move to higher performance ones, so more recent ones than SIFT. Then we'll talk about binary versions of these features, which are more effective and faster. And also about dataset benchmarks and software that implements them. And finally, about applications. OK. So a little bit of a walk down memory lane. What are these classic local features? For a SIFT, I've mentioned it a lot. Then surf, which is a more efficient SIFT. And then a few more recent ones, especially for dense matching, which is DAISY, which is a dense SIFT, if you want. So how does the original SIFT pipeline work? Well, you take an image, you detect interest points or corner points, points where the signal is interesting in some sense. Then at every one of these points, you compute a local orientation. And given that orientation, you compute the feature descriptor that is meant to be invariant to rotations and translations of the image. So what are these interest points? Well, in an image, typically you will have edges, you'll have corners, and you'll have what I'm calling here uniform areas or blobs. SIFT is really looking at blobs. That's what it's trying to find, little regions that have a more or less uniform gray level. And the idea behind it is that of using something called the Laplacian of Gaussian, which is a sum of second derivatives of the image. So that's, of course, implemented with Gaussian convolutions. And because they are Gaussian convolutions, the size of the operator depends on the sigma you use for your Gaussian. You can make it narrower or wider by changing sigma. So in a very simple case, like this one, three black dots, three versions of the operator of different width. And if you look at the response of this operator to these toy images, you have this response with what's interesting about this is that the Laplacian responds very strongly at a particular scale. So it responds at a characteristic scale. And that's something that SIFT is going to exploit again. So if you take a Laplacian centered where the yellow circle is, and you look at the response when you vary the scale, you have a peak for a particular size, a particular sigma. But you also have a peak if you move it off-center. The response will also decrease. And so in the end, what an interest point is a point that's going to be a maximum both in the xy dimensions, but also in the scale dimension. If you imagine you take your image and you blur it more and more and more and you stack these things, an interest point is going to be a maximum in this stack of images. So basically, that's what a SIFT interest point is. And the good news, which I don't have time to discuss, of course, I've only shown this for circles, but it works remarkably well for much more irregular shapes. And an additional thing that has been observed is if you use the Laplacian, you have to compute second derivatives, which is kind of expensive. It turns out you don't even need to do that. You can compute difference of Gaussians, and the difference of Gaussian operator is as shown by the red and blue curve on the left. They are not exactly the same, but they are so close that given the kind of precision we operate at, they are all, for all practical purposes, they are the same thing. And you can do this whole thing using difference of Gaussians, which is what David Lowe exploited when he implemented SIFT a long time ago. He was working in this pyramid of images, looking for maxima in 3 dimensions, and doing it very efficiently. Then, of course, there's a number of tricks added to this, which is since you cannot sample at every scale and the images have a finite resolution, you can refine by looking at the response the response at various integer value of the pixels and interpolate to get better values of your key points. That matters. If you want precise geometry to do bond adjustment, that matters, to have the points exactly where you want them to be. And then there are a number of tricks to get rid of points, of interest points that look like edges as opposed to blobs. So what this does, this is the first step of the SIFT pipeline, it gives you the interest points. Once you've done this, what you are going to do is, given the interest point, you are going to histogram all the orientations around that interest point and look for the dominant one. And that dominant one is going to become essentially your reference, and all other orientations with respect to that dominant are going to be in the neighborhood are going to be expressed as differences with that reference orientation, which is going to allow you to build the SIFT descriptor, which is you take a patch, an image patch, which is on the left, and you group it into blocks. And within each block, you compute a histogram of orientations, or of difference of orientation with respect to the canonical one. And essentially, this is what the SIFT descriptor is, and it works really well. Incidentally, I mean, all of this is done with convolutions and the like. So it's not that surprising that now that we are in 2017, you can reformulate that deeply, because essentially that's what deep nets are. So what the deep nets are going to do is redo what David Lowe did in his head 18 years ago, and hopefully doing a little bit better because it will optimize everything. But fundamentally, it's not going to do anything all that different. Okay, so the next one that's been very, very influential is one called SURF. And SURF is essentially a speeded up version of SIFT, where what you do is, instead of doing Gaussian convolutions, you use hard wavelets, which essentially are blocks of zeros and ones. And if you do it well, which they did, you can get 3 to 7 times performance improvement with very little loss in matching accuracy. So just to give you very quickly an idea, still, if you go back to Laplacian, you have the second derivative masks at the top, represented if you use the Gaussians to compute them. It turns out that you can approximate them very well with blocks of zeros and ones. It does almost the same thing, but it can be computed much, much faster, especially if you use integral images. Oh, I'm lost. Sorry. So if you compare SURF and SIFT, where am I? Okay. So if you compare SURF and SIFT, what SIFT is doing really, it takes an image, it builds a pyramid by doing Gaussian convolutions and then subsampling. And at each level of that pyramid, it uses a filter of the same size. SURF does it the other way. The image doesn't change. You don't subsample. But the masks become bigger because, and what allows you to do this without spending too much time doing it is the use of integral images. Okay, so these are the popular ones. There have been others, of course. So here is one. If you are really concerned about going fast, instead of doing either SURF or SIFT, which still involve convolutions, you can simply take a point and look for its neighbors and just check whether its gray level is greater or smaller. Turns out that if you do it right, that's discriminative enough, and you can get a pretty good feature point detector this way. Or if you want to do the reverse, which is to match densely. So SIFT and SURF are designed so that you only do matching at a small subset of interest points. But there are applications for which you want to match actually the whole image, especially, for example, stereo. So there you can actually do something that's directly inspired by SIFT, but slightly different, which is you are going to look at gradient distributions in concentric circles of increasing radius. And it turns out that this shape is something you can compute very effectively just with 1D convolutions. It's all 1D Gaussian convolutions. And you can compute this DAISY descriptor everywhere very quickly. And the advantage of doing this is, so this is the computation pipeline. And the advantage of doing this is if you want to match, say, a stereo pair like this one. This is a pair of images from a very classic benchmark. And this is the ground truth, so the depth. What you can do is you compute the descriptors at every point, and then you do standard stereo matching. And if you use DAISY, you get something like this. If you use SIFT, it's actually a bit easier. And it's also slower because SIFT is not designed to compute densely, so you don't exploit the fact that some computations can be reused again and again and again. And both are actually better than a lot of the other applications. So that was a very quick overview of the classic methods. And now I leave, it's Bin who's doing the next, I'll leave Bin to show you something a bit more modern. So thank you. Sorry?
Do you still be here or going on?
I'm going to go around, but I'll be back at 5.
Okay.
Oh, that's...
Good afternoon, everyone. I'm Bin Fan from the National Laboratory of Pattern Recognition, Chinese Academy of Sciences. In the first part, Professor Fa has given us a brief introduction of the classical local features. In this part, I will focus on the recent advances of this topic. More specifically, I will focus on the modern descriptors designed for the high matching performance. These descriptors include both the traditional handcraft ones and the recently popular learning-based ones. Let's first look at the handcraft ones. This section covers several new techniques proposed in recent years for the shifter improvements. These include, first, I will introduce a nonlinear scale space as an alternative to the widely used Gaussian scale space. as the one used in SIFT or SURF. Then I moved to the intensity order-based pooling method and introduced several local features based on intensity orders. Finally, I will show how to incorporate information of multiple scales to further improve descriptors' performance. The KZ feature proposed in ECCV 2012 is a typical alternative to the widely used SIF and SURF by using the nonlinear scale space instead of the widely used Gaussian scale space. Compared to the Gaussian scale space, which is a linear one, a nonlinear scale space could preserve more details of the edges. Thus, it is expected to have a better localization accuracy. KZ adopts an identical pipeline for feature detection and description to the SURF, which has been introduced in the first part. The only difference lies in the construction of scale space. In SURF, it adopts the Gaussian scale space, while in SURF, it uses a nonlinear scale space. At the core of a nonlinear scale space is a nonlinear diffusion filtering method to the image. Before introducing how to construct a specific nonlinear scale space, let's first look at an example of how images may look like in a Gaussian scale space and a nonlinear scale space, respectively. In the first row, it shows the images of a Gaussian scale space. It can be seen that the images in a Gaussian scale space responds equally to the object boundaries and the flat areas, so for the noise and the details. When scale involves, image structures become more and more blurry. On the contrary, as shown in the bottom row, a nonlinear scale space responds differently to the object boundaries and the smoothed areas. When scale involves, image structures with strong edges responses are not affected. As a result, by using a nonlinear scale space for feature detection, we can expect it to have a better localization accuracy. This is the motivation of using nonlinear scale space. To construct a nonlinear scale space, KZ describes the time steps of the nonlinear scale space in a similar way to the Gaussian scale space. They are arranged in octaves, each of which contains sublevels. Then, these pixel units are transferred into time units as time steps in a nonlinear scale space. Finally, a nonlinear scale space is constructed for these time steps by iteratively applying nonlinear diffusion filtering to the input images in a scheme named as the additive operator splitting. In the KZ paper, it studies 3 types of the nonlinear diffusion filtering. All these operations are based on the local gradient strength. According to the formulation of additive operator splitting, it can be found that it has to solve a large system of linear equations in each time step. This operation is computationally expensive. To construct a nonlinear scale space very fast, the authors of KZ have also proposed another approach to compute the nonlinear diffusion filtering. This approach is called the faster explicit diffusion. It computes images of different time steps in an additive way and does not contain any time-consuming stops. This approach is proposed in BMWC 2013. Besides using nonlinear scale space, using intensity orders for feature description has proven to be effective in the past years. At the core of this intensity order-based method is a feature pooling method based on intensity orders. For the traditional methods, such as SIFT and SURF and so on, they have to rely on geometric locations to aggregate low-level features to construct the descriptor. As shown in this figure here, each color represents a special point area based on the geometric locations. Such a geometric location-based spatial point method is unreliable since it has to align the locations according to an estimated orientation, which is usually not stable. To solve this problem, the intensity order-based point method is proposed. Briefly speaking, it first divides the local region into several subregions based on the pixels' intensity orders. Then, for each of the subregions, the pixels' low-level features are accumulated to obtain a histogram, such as the histogram of the gradient. Then these histograms are concatenated together and normalized to form the descriptor. As shown in the figure here, each color represents such an intensity order-based point region. This intensity order-based spatial point method is rotationally invariant in theory. That is, no matter how the local region rotates, it always accumulates low-level features from the same pixels. So the obtained descriptors is rotation invariant too. Meanwhile, using the intensity order is also very robust to the monotonic intensity changes, which further increase the robustness of the obtained descriptor, especially for the illumination changes. Combined with this kind of this feature point method, it can be used with various low-level cues, which I will introduce in the following. Firstly, we propose to use a low-level feature similar to the one used in SIFT. It is a gradient orientation map computed in a local coordinate system. As shown in the left figure here, for each pixel, a local coordinate system is constructed so as to achieve the rotation invariance. So in this coordinate system, we compute low-level features and obtain its rotation invariance. So that's for the constructed descriptor, which we call Malov. We further use the rotation invariant center surround OBP as another kind of low-level feature to construct the other kind of descriptor called Merit. Note that it is also computed in a local coordinate system to achieve the rotation invariance. To further improve the distinctness of the generated descriptor, a strategy of using multiple support regions has been proposed in Malov, along with the Malov and the Merit. The basic idea is very simple. We know that for two non-corresponding key points, it is possible for them to have similar local patches. However, it is less likely for them to have similar local patches at various sizes, as shown in the middle figure here. As a result, we simply use multiple support regions to compute descriptors and then concate them together to form the final descriptor. Instead of relying on traditional low-level features, as I have used before in Malov and Merit, we also proposed a new kind of low-level feature, named as the local intensity order pattern LEOP, to incorporate the locality ordinal information along the pixel. Given a pixel, we also construct a local coordinate system for it to achieve the rotation invariance. Then take out its 4 labeling points in this coordinate system. Their intensities are sorted and further mapped into a 24-dimensional one-hot vector as the LEOP feature. With this kind of low-level feature and using it in intensity order-based polling framework, we finally obtain a descriptor, also called the LEOP. Although LEOP is very robust to the brightness changes since it relies on the intensity orders. However, the intensity orders is somehow not robust to the noise, which further limits its performance. To solve this problem, we further propose another method called OIP. It quantizes the intensities according to the overall intensity distribution in a local patch. The quantization results are used as a kind of low-level feature to construct the descriptor, also in the framework of the intensity order polling. So the problem is how to quantize. A naive solution is to use the average quantization. This approach quantizes intensities equally. However, according to our experimental results, the quantization result is largely related to the ordinal polling region we used in the intensity order-based polling framework. As shown here, this is a statistical result. Such a correlation between the low-level feature and the special polling region will limit the discriminative ability of the generated descriptor. As a result, we cannot use this method. Alternatively, we propose to learn the quantization percentiles for each ordinal polling region, respectively. The idea is to learn best quantization percentiles for each polling region so as to make them distributed equally for each ordinal polling region. Thus, the enhanced discriminative ability is expected. Given the learned quantization, the procedure of constructing an OIP descriptor can be summarized as these 5 steps. For each pixel in a local patch, it is represented by an n based number, which is further mapped into a m power n dimensional one-hot vector. These vectors, similar to the LEOP, are polling into a descriptor in the framework of the intensity order-based polling. To further improve the robustness and the distinctness of the descriptor, some researchers have proposed to use information of multiple scales. For example, as I have introduced before, in Manoff and Merit, we already use multiple scale information to compute the descriptor, and then concate them together to form a final one, very distinctive one. Another way to use information of multiple scale is to directly polling them together across different scales. This is exactly what the DSP shifter does. It adds all shifter descriptors across all scales from one single descriptor. Alternatively, we can also suppose that the shifter descriptors of a key point across different scales lie in a feature space. Then we can use the basis of the feature space as a feature representation to construct the descriptor. Up to now, the methods I have introduced are all handcrafted ones. In the following, I will introduce how to learn high matching performance descriptor with data-driven method. This method includes the traditional machine learning method and the recently popular CNNs. In ECCV 2014, we have proposed a method called the Affine subspace representation to unsupervised learning of the local image descriptor. The core idea is to learn a subspace representation of the patch under different viewpoints, so as to incorporate the robustness to the viewpoint changes in the descriptor. Given a patch, we first apply a Affine warping to it and generate several patches under different viewpoints. Then, for each of these Affine warped patch, a PCA vector is extracted as its feature. You can also use other feature. These vectors are supposed to lie in a feature space. As a result, we apply PCA again to these vectors and use the extracted basis of the subspace as the feature representation. However, exhaustively applying the Affine warping to all patches online is extremely computational expensive. To address this problem, we proposed an efficient computing method based on a linear approximation, moving most computations to the offline. For a patch, it can be approximately decomposed and linearly it can be approximately decomposed into several patches. This is cheap. Then, due to the linearity, applying Affine warping and PCA projections to the original patch is identical to applying these procedures to the basic patches and then linearly combine them together. Note that in this way, applying Affine warping and PCA projection to the basic patches can be pre-computed online. For a new patch, we only need to decompose it and then combine the corresponding projections of the basic patches. As a result, the computational burden is largely reduced. Based on the summarization of the handcrafted descriptors, Matthew Brown et al. Have proposed to learn the co-components of a feature descriptor by optimizing the areas on the RC curves. These core components include low-level feature extraction, spatial polling, and feature embedding methods. According to the published result of the handcrafted descriptors, they first proposed to learn several methods of low-level feature extraction, spatial polling, and feature embedding. Then they apply the power optimization to find the best combination of these components by maximizing the areas under the RC curves, of course. For the low-level feature, they have used the gradient-based features like the one used in Swift or Surf and Daisy. They also used the steerable field banks as the low-level feature. For the spatial polling, they adopt Swift-like, Daisy-like, and Graph-like configurations. For the feature embedding methods, they have tried both the unsupervised and supervised subspace learning methods. Their optimization results show that the best performing local descriptor is the one using the steerable field banks as the low-level feature and use the Daisy-like spatial polling method. The second best one is actually a specific kind of Daisy descriptor that Professor Fa has introduced in the first part. It uses the gradient orientation map and of course also uses the Daisy-like spatial polling. For the feature embedding method, it's interesting to see that the unsupervised PCA is better than the supervised one here. Following Matthew Brown's work, Simeon et al. Have reformulated the learning target as a convex one with the sparse construct. In this work, they only focus on the learning of spatial polling and the feature embedding methods. The low-level feature is fixed as a kind of the normalized gradient orientation map. In their formulation, each polling unit contributes to a part of the descriptor. And the learning target is to select a small number of polling units from a large number of the possible units by imposing a sparse constraint on the margin-based objective. Here, the margin means that the descriptor distance of the matching pairs should be less than the descriptor distance of the non-matching pairs by a predefined margin. The merit of this work lies in its convex property, which ensures that the global optimized solution could be reached. Their experimental results do show a great improvement over the bronze work. And now let's look at some deep learning methods for the patch matching and the patch description. The pioneer work of using deep learning to the patch matching problem is perhaps the matchlet proposed in CVPR 2015. It simultaneously learns the descriptor and the metric. Accordingly, it contains two networks. One is a Siamese feature network, which is in charge of extracting feature descriptors of the two input patches, while the metric network is on top of the two features and outputs their matching score. The feature network is consisted by several convolutional and Pauling layers, and the metric network is consisted by 3 fully connection layers. Once the nets have been trained, matchnet can be directly used for patch matching. This operation requires testing all possible pairs, which computes descriptor of one patch many times. To reduce such a redundant computation, a two-step scheme is proposed. Firstly, it takes out the feature network of the matchlet to extract descriptors for all patches. Then, according to the matching candidate, it combines the descriptor pairs and then input them to the metric network, finally obtain their matching score. Such a two-step scheme can effectively avoid the redundant computation of extracting patch descriptor by the feature network. The deep compare is proposed at the same time of the matchnet. It studies the possibility of using deep network to learn similarity function for a pair of patches. For this purpose, it has proposed several different kinds of network architectures and tested their performance. The authors of Deep Compare first proposed a two-channel architecture as the similarity function. In this network architecture, it takes two patches. The two input patches are stacked together and served as two channels of an input image to a CNN. This two-channel input image is then forwarded to a CNN with several layers of convolution, Pauling nonlinear actuation, and finally a fully connection layer to output the similarity score of the two input patches. Such a two-channel architecture is highly coupled, and there is low direct lotion of the descriptor. As a result, it has to traverse all patch pairs when using it for patch matching, and cannot reuse the descriptor of each patch. Apparently, it is very time-consuming. They also proposed a same network architecture to the matchnet, which I have introduced before. Moreover, they have proposed a two-stream strategy to deal with the patch matching problem at two different resolutions. The two input patches are divided into two streams. One is a central stream operating on the central part of the input patches, while the other is a surrounding stream operating on the whole part. These two streams go through two feature networks separately and then are concatenated together to output a similarity score of the two input patches. Their experimental results show that such a two-stream strategy can effectively improve the network's matching performance. For the network training, both matchnet and the deep compare are based on the cross entropy loss of individual pairs. Apparently, such a loss ignores the global distribution of the training dataset. Some researchers have argued that a better loss function should model in the global distribution of the training dataset. As a result, Kumar et al. Have proposed to train a deep network with the global loss. In CVPR 2016, the core idea is to reduce the proportion of false positives and false negatives in the two distributions of the positives and the negatives. As a result, their learning objective is to minimize the variance of the positive and the negative distributions together, and then, at the meantime, to maximize the margin between the mean values of the positives and the negatives. Following this basic idea, they have designed two specific global losses and one classical local loss based on triplet samples. When one wants to directly use the network's output as a feature descriptor in a Euclidean space, it is suggested to train a network with the first two losses. One is a global loss defined on the Euclidean space, while the other is a local loss. For comparison, they have also obtained a method by only using the local loss to train a network. Their results show that by adding the global loss to the objective, it can lead to better performance. On the other hand, when one can use the CNN network with additional magic layer, it is suggested to train a network with the third type of loss. It's a global loss defined on a similarity score. Kumar et al. Have tried with the two different network architectures of the deep compare by using this type of global loss, and their results show that using global one is much better. For all these deep learning methods I have introduced, they have to be combined with magic layers so as to achieve the good patch matching performance. However, in many applications of patch matching, it has to conduct large-scale nearest label search. In this case, it has to use the brute force search when we need to match the descriptor with the magic layer. This is time-consuming and impractical in many cases. In order to use the faster approximate nearest label search methods, such as the KD tree, we need to match the descriptors in the Euclidean space directly. For this purpose, there have been proposed several deep learning methods that learn a patch descriptor directly in the Euclidean space. The deep disk proposed in ICCV 2015 is an early work under this motivation. This method in itself is very simple as it utilizes the widely used pairwise hinge loss and adopts a classical CNN architecture. Its main contribution is a network training strategy based on mining hard samples. Such a training strategy can effectively alleviate the problem of the extremely unbalanced training state in the patch matching problem. This is the network architecture of the deep disk. It has 3 convolutional layers followed by activation and polling layers. It takes an input patch of 16.4 by 16.4 and outputs a 128-dimensional vector as the descriptor. For the patch matching problem, large amount of the negatives are easy to be distinguished. The author have found that in this case, the network won't be easy to saturate. In this case, the network In this case, the loss gradient almost approaches 0, so the network cannot be further trained. To address this problem, they have proposed a hard sample mining technique to train a network. The idea is to forward enough samples to the network and then only using the samples with large errors to compute the loss gradient so as to update the network parameters. Another work of using deep learning to learn the patch descriptor in the Euclidean space is the T-fit proposed in BMWC 2016. It is also based on the triplet samples and effectively utilizes the exchangeability of the two matching patches in a triplet. The basic learning objective is to make the smallest negative distance within a triplet be larger than the positive one. As a simple illustration of this idea, let's look at the right figure here. It shows 3 samples in a triplet, 2 form a matching pair, and the other one is the non-matching one. If we can make the delta star be larger than the delta plus, obviously the delta minus will also larger than the delta plus 2. Following this objective, they have proposed 2 specific losses. One is a ranking-based, while the other is a ransion-based. In practice, the author have pointed out using the ranking-based one is better. It is worth to note that in this method, it uses a very simple and shallow convolutional neural networks as the feature extractor. It only uses 2 convolutional layers. As a result, T-fit is very fast to compute. In a GPU implementation, it needs about 10 microseconds to compute, which is comparable to the fastest brief descriptor in a CPU. Such a property makes it very suitable for the online applications. In this year's CVPR, we have also published one paper about learning a discriminative patch descriptor in the Euclidean space. Our method is called L2LAT and can be directly used as a drop-in replacement to the traditional descriptors such as SIFT and SURF. It takes a fully convolutional architecture with 7 convolutional layers, each of which is followed by a batch normalization layer. The L2LAT takes an input of 32 by 32 patch and outputs a 128-dimensional vector after the local response normalization. To further improve its performance, we also adopted the strategy of the 2-stream and proposed the center-slump L2LAT. The 2-stream strategy is similar to the one used in deep compare. The core ideas of L2LAT contains these 4 parts. Firstly, it utilizes a progressive sampling strategy in the training stage. This sampling strategy ensures a batch to contain lots of negatives while only a few positives. This is in accordance with the matching scenario. Secondly, it incorporates the concept of the relative minimal distance of the matching pairs. This models the characteristic of the nearest label matching. Thirdly, it also makes use of the additional supervisory information from the intermediate layers so as to improve the generalization ability of the obtained descriptor. Finally, the compactness of the named descriptor is taken into consideration in order to reduce the risk of overfitting. Let's first look at the sampling strategy. In each iteration, it first samples P matching pairs from the training dataset. Then, by randomly selecting one patch from each matching pair to form non-matching pairs, it finally obtains many negatives and only a few positives. Apparently, such a sampling strategy contains more negatives than widely used pairwise and triplet samples. Based on the summarization of the core ideas I have summarized before, the learning objective of L2LAT contains 3 parts. For the first part, let's denote D as the descriptor distance matrix of the patch pairs. According to the sampling formulation, in the ideal case, DII, which is the distance of the matching pair, should be the smallest one in the ith row and also for the ith column. As a result, we apply the softmax to the columns and the rows respectively to the distance matrix and obtain 2 similarity matrices. Then we use the entropy-based loss as the E1. Note that here in the loss we use the Euclidean distance to measure the descriptor distance, so that our length descriptor can be directly used in the Euclidean space once it has been trained. For the second objective, it is about the compactness of the length descriptor. By compactness, we want to make the different elements of the length descriptor as small as possible. The second learning objective is similar to the first one. The difference is that the first one is focused on the output descriptor, while here the third one is focused on the intermediate feature maps. However, the basic idea is identical. That is, for the matching pairs, we not only want the final descriptor, but also want the intermediate feature maps should have the largest relative maximal similarity. Since the similarity is defined by the inner product, it uses the feature maps after the batch normalization layer. It has to be aware that such an additional supervisory information from the intermediate feature maps cannot be overused. According to our experimental results, it only works with the first and the last convolutional layers. When using all the feature maps, it will damage the length descriptor, as shown by the curve D here. We also studied the performance of batch normalization layer and find that using the fixed batch normalization parameters is slightly better than the length one. As a byproduct of the L2LAT, we further obtained a binary L2LAT is a kind of the binary descriptor. This is because that we found that the output value of the L2LAT approximates a zero mean Gauss distribution as shown in the left figure here. Such a property is what a good descriptor requires. As a result, we directly apply in some function to the L2LAT and obtain the binary L2LAT. As shown in the right figure here, the mean values of most binary L2LAT approach 0. This demonstrates that the discriminative ability of the L2LAT is very good. So far, the methods I have introduced are all for descriptor learning. However, is considering only descriptors wise? The answer is not. In CVPR 2016, E et al. have pointed out that the orientations of local patch plays a very important role in the problem of patch matching. This has also been pointed out in previous works about the notation invariant descriptor. As a result, instead of the dominant gradient orientations, they have proposed a CNN architecture to learn the orientations of feature points. This is the learning framework of their method. An orientation estimator is implemented by a Siamese CNN network. The learning target is to minimize the descriptor distance of the corresponding key points. That is, the object is to is to learn the orientation for descriptor matching. In this work, they use the shifter descriptor, although it can be used with any other kind of descriptor. Since shifter is non-differentiable, in a CNN network, it has to pre-compute all the shifter descriptors for all orientations so as to use the numerical derivatives for the network training. This result shows the improved result with the named orientations. The right two corners are the result with the named orientations by this work, while the two bars next to the right two corners are the corresponding methods with the traditional dominant gradient orientations. Besides learning to assign orientations, E et al. Further proposed a whole pipeline for the feature description, which includes feature detection, orientation estimation, and the feature description. This work, named as the Land Invariant Feature Transform LIFT, is essentially based on the previous work of their team. All these previous works on the feature detection, orientation estimation, and the feature description are CNN-based. LIFT just combines them together with the differentiable connectors so as to learn all the steps in an end-to-end manner. To train the whole pipeline, it requires various patches for the different components. For example, for the feature detection part, it has to distinguish the key points from the non-key points, while for the orientation estimator, it has to output similar orientations for the corresponding key points. For the description part, it has to minimize the descriptor distance of the matching key points, while at the same time to maximizing the descriptor distance of the non-matching key points. Due to these reasons, LIFT proposed to use a quadruplet Siamese network for the network training. It takes 4 patches at once as input. Among them, 2 patches are from a pair of corresponding key points. One is from a non-corresponding key point, and the last one is a patch from the non-key point. By Siamese, it means that the network shares parameters for different patches. The learning objective of LIFT contains 2 parts. One is a Euler function, while the other is a pairwise one. The Euler function considers the ability of detector, while the pairwise one considers the descriptor distance, where the detector and the orientation estimator are implicitly considered. Although this loss is differentiable, it is hard to change because different components tend to compete each other. As a result, E et al. Have proposed to train the whole pipeline in a smart way, one component by one component. Specifically, they first train the descriptor network by using the input patches. Then, by fixing the descriptor network, they train the orientation estimator, and so for the detector network, they use the already named descriptor network and the orientation estimator. Finally, after all the components have been trained, it is optimal to fine-tune the whole pipeline. This figure shows the improved result when using the LIFT. Each component is made for each other. The blue bar is the result with the shift as baseline. By replacing the shift descriptor with the LIFT descriptor, we can observe a performance. By further replacing the shifter key points with the LIFT key points, a further improvement is obtained. To conclude this talk, I would like to highlight several points. Firstly, for the patch-level dataset, nowadays the learning-based method has generally outperformed the handcraft ones. This is especially for the bronze dataset. The performance of the learning-based method has almost saturated. However, this is not the case of the image dataset, where the performance gap between the learning-based method and the handcraft method is not so significant. There may be two reasons. One is that matching image-level dataset not only involves a local descriptor, it also requires a good detector. While the other reason is that there are many key points are not matched by the structure flow motion algorithms, so this kind of variance is not considered in the training dataset of a learning-based method because almost all the patch-level datasets used for the learning-based method training are built up on the structure flow motion algorithms. The second point is that the CNN-based method has dominated the learning-based ones due to the large learning ability of the CNNs. And now, the trend is to learn a patch descriptor directly in the Euclidean space for its wider applications. Finally, as a start point of the image matching, feature detector plays a very important role. However, its learning problem has been largely ignored. How to learn a good detector with high repeatability and distinctness should receive more attention in the future. That's all my talk. Now let's have a coffee. Oh, we still have time. So, okay, do you have any questions? Okay.
Back to the slides on L2net. I have some questions.
L2net, yeah. Which one?
So first, this one, I'm wondering, like, what's the intuition about the structure of different convolutional layers that you use? For example, I noticed that, like, so you start from the bottom to top, right? So it's 8 by 8 and 3 by 3.
Yeah.
So is there any intuition on how it shows this architecture, or just from empirical evidence? Like 8 by 8 is not a usual curve. Just like in the usual.
Yeah, the motivation is that we just want to use a fully convolutional architecture, and then we try with different channels and the parameters of the convolutional kernels and find out this works. Yeah.
Why
Okay.
do you think that the difference between image level descriptor and image level descriptor using CNN does not have big difference between corrected descriptor?
As I have mentioned, I think for matching the patch level dataset, it has also involves feature detector. And at this point, the feature detector are not fully suggest. So the performance, I mean, even you have a very good descriptor, but in the feature detection part, you don't have enough repeatability. It will also lower the final performance of the matching matrix. Is that right?
For the progressive sampling that you mentioned, L2net,
Yeah.
is it different from the n pairs loss that was proposed recently for embedding frame? It seems very similar to that. Do you know that?
Pardon?
So there is a new deep metric learning framework that was proposed at the first MIPS last year. It's called n pairs loss. It seems very similar to this
Yeah. The sampling method is, I think, is similar to the one. I think you mentioned that one. Yeah, it's not in EPFL, maybe in ICCV or CVPR. I not remember very clearly. It's similar. It's similar. By lifting all the chaining, all the samples in a chaining batch, all the combinations. This is the basic idea. That is because for the we think is essential for the matching problem, because for the matching we always have to face many negatives and only a few positives. If we can utilize all the possible negatives in a batch, we could expect better performance after chaining. Yeah. How about coffee break? Okay, let's get together at 4 o'clock, and then Professor Jiwen will give us a.
Okay, good afternoon, everyone. Welcome back to our tutorial. I'm Jiwen Lu. I'm from Tsinghua University, and now this is the second part of our tutorial. In the first section, and Professor Fa and Dr. Fan has introduced some local feature, basically some handcraft and some learning-based. And in this section, I will focus on binary feature learning for visual recognition and search. And because the title of our tutorial is feature learning, feature extraction and learning for computer vision, in this part, I will focus on visual recognition and search because these two topics are very, very important in computer vision. So for visual recognition, the basic idea is we want to recognize the objects or the video or the activity or a human in image or video. So one typical example in visual recognition is face recognition. For face recognition, there are two different settings. One is face verification. Given a pair of face image or video, we want to determine whether they are from the same person or different. This topic is very hard over the past few years, and there are many face recognition startup company in the world, especially in China. The second example in visual recognition is person re-identification. We want to re-identify, or we want to recognize the person across multiple camera or say in the camera network. That to say, we installed many cameras in the large-scale scene, but this camera may there may be no overlapped areas in the camera network. So we want to recognize the person across different camera. For example, the person working in this camera and then he is walk out in the scene and moved to another camera. We want to recognize his identity based on the body image or video. So person re-identification aims to recognize the human identity for the working image or videos. The last example is image classification. This is a well-known topic in computer vision, like an ImageNet competition. We want to recognize what is an object in the image. Besides visual recognition, there is another topic is visual search. So the basic idea and the basic difference between recognition and the search is for the search application. Most of the cases we may not care about the top 1 recognition rate. We just care about the top ranked search results. The key application of visual search is in the large scale visual search. For example, there may be thousands of image in the website or in the internet. For example, we are attempting CVPR conference. We take a capture. We capture an image in the shuttle and and then we upload in the website. We want to recognize what is the sim or what is the contact in the street. So the key idea of visual search is we want to match the query image and the large scale database to based on the visual appearance feature. So local feature is also very important in this topic. So in these two applications, we have one key objective. We want to develop some machine learning techniques to obtain the efficient feature descriptors. So the basic solution is we want to achieve. So for binary feature representation, the key advantage is we can make the feature representation very efficient, and then the matching stage can be very, very fast. So there are two different types of binary feature descriptors. One is handcraft, another is learning-based. For handcraft, sometimes we use some human knowledge or some prior knowledge to develop some strategies or rules to extract binary features. For example, we can extract some local patch and then do some comparisons. Then we can get some binary features or binary stream for this image patch. For learning-based feature descriptors, we want to develop some learning algorithms to extract the features for the given pair, given image or given videos. So here is the one example of the handcraft features. So in this image, we can select some local part or local patch, and then we can do the comparisons. We can get 1 or 0, and then we can, if we select many bits, and then we can get many binary codes. The second example is binary feature for visual recognition is based on learning techniques. So let's come back to see what is the conventional visual recognition system. For conventional visual recognition system, there are two stages. One is we can train a model or learn some features offline, and then we can get the feature representation for gallery samples, and then we can get the feature representations for to store these features in the database. So in the testing stage, we are usually obtaining the samples online, and then we want to extract features for probe samples, and then we can do matching. Considering the database is larger, sometimes we need to make the storage efficient and make the comparisons fast. So sometimes we need to use binary features to achieve this goal. So binary feature representations usually have two advantages. One is it can usually make present high storage efficiency because the binary features can save more space to store the feature representations. The second one is the matching speed. Matching speed is usually faster than the real valued features. So that's the reason why binary feature representation is popular in this area. So the key reason of the matching speed is why binary feature is fast is because previously if we want to use real value to do the matching, sometimes the equivalent distance is usually used. For binary feature, we usually use the Hamming distance, but Hamming distance can be performed, or the similarity can be computed in the Hamming space, and the AND and OR operations can be used, so the computation speed is very fast. So in the computer vision area, a very popular local binary feature is a local binary descriptor. This paper was published in ECCV 2024. And the paper, this idea was first used for texture classification, and then it was introduced for face recognition. So now I will introduce the basic idea of LBP features, local binary feature descriptor, LBP features. So for LBP features, given an image, we first sample a patch for the image, and then we can compute or we can compare the elements or the pixels within this patch and compute the difference between the pixels around the central pixel and the difference between them, and then we can compute. If the difference is larger than 0, then we can get a one code for this element. Similarly, this is 1. This is 0 because 1 is smaller than 4. So we can get a binary stream around this part. And then we can, if the size is larger, we can get many binary elements around these blocks. So we can get a binary stream for this patch. Then we can decode this binary stream into a number. In this paper, it used to convert this binary stream into a discrete number. To say, we encode this as this. So this is the basic idea of LBP feature, especially the local part extraction. So what's the key limitation of LBP feature? Even LBP feature is very popular and achieve many successful in face recognition. So let's come back to the key idea of LBP. So if we using this feature extraction and encoding strategies, sometimes we can find this approach can usually obtain the uneven bin descriptor for LBP. For example, we take the phase dataset for Farad dataset to as an example to show the bin distribution for LBP feature. So if we can, in the training set of the Farad dataset, it contains 1,002 images. So we can compute the binary stream for each patch within the dataset, and then we can find some bins. The occurrence of these bins is usually uneven. For example, there are many bins have more elements or more occurrence, but some bins are very less or fewer. So what's the disadvantage of this observation? For this observation, we find some bin may contain discriminative information, but some bin are less discriminative. Based on this observation, what we want to do is we want to learn a local binary feature descriptor which can achieve or which can make this distribution more even than this one. So this is the key idea. So based on this idea, we proposed a method called compact binary phase descriptor for phase recognition, and this paper is published in 2015. So what's the key idea of our approach? The key idea of our approach, we first give a phase image. We can get some patch or sample some patch within each image, or even the whole training set. Then for each patch, we can first get a PDV feature vector. What's the PDV feature vector? It's almost the same as LBP. So we can compute the difference between the elements around the central pixel and the central pixel. Then, for example, we can get some positive value and some negative value. But even we have a positive value and a negative value, but we didn't do the thresholding at this stage. So based on this PDV value, what we want to do, usually if the sampling size is larger, this PDV value or this PDV feature vector maybe is a high dimension vector. For example, if the size is 7 by 7, the feature dimension of this PDV value is 48. If the size of the patch is 9 by 9, the PDV value, the feature dimension of this PDV value is 80 by 80. Sometimes this PDV value, we find that there are some redundancy in this PDV value because some neighboring pixels usually have some redundancy information in the image patch. So what we want to do is we want to match this high dimensional PDV feature vector into a low dimensional binary space, a binary feature descriptor. What we want to do is we make this high dimensional feature vector, PDV feature vector, real valued to the local binary feature vector, binary code. We achieve some objectives. For example, first, the redundancy of this PDV value can be well removed. Second one is we can make some bin of the distribution of the bins or this binary code are much easier than I mentioned just now. So for the training set, we can get many compact binary codes. Then we do the clustering to learn a dictionary to get a code book or for the training set. Then given a PDV value, we first get a binary feature representation, and then we can encode it using this code book, and then the whole phase image can be represented as a feature, histogram feature. So for the test sample, the same. We first extract a patch and then compute the PDV value, and then using the PDV CBFD, the learn the projection, and we can get a local binary feature vector, and then we encode this local feature vector as a histogram image. So for the training set and testing set, each sample is represented as a histogram feature vector, and then the similarity of the two histogram sample vectors is computed to mirror the similarity of two phase images. Then we can do phase recognition based on this idea. So what's the key objective of our CBFD value? The key objective of our CBFD is we want to have some optimization over this projection. So we have three terms based on our method. First, we want to remove some redundancy information of the PDV value. The second one is we want to preserve the energy of the view value of the PDB vector to the binary code. The last term is a balanced beam. What's the physical meaning of balanced beam? For example, if we have many beams of the binary feature vector, we want to make sure that each beam is as balanced as possible. For example, if we have 1,000 patch, we expect 500 patches. The first bit of 500 patch was represented as 1, and the left 500 patch was represented as 0. In this case, the first beam can contain more discriminative information as much as possible. So based on these 3 terms, we can do the optimization. So what's the advantage? Sorry.
Can you explain a little more the 3 parts of the loss? What do you mean by redundancy removing energy preserved?
The first term is remove the redundancy. Redundancy.
What do you mean by that?
Redundancy. For example, if this is a real value, right? Real value features. So this is the binary feature vectors. So we compute this is the binary. This B can be computed using RW. So this is the obtained binary code. Here, mu k is the mean information of the learned binary code. So this part we can compute. This part is energy preserving. What is energy preserving? That is to say, for the view value the feature vector projecting the binary feature vectors, the key energy can be preserved. It's similar to the PCA criteria. So based on these 3 criteria, we can find, okay, the learned binary code or the learned the binary representation or the bin distribution is much evil than before. Even they are not equally the same, but we can find the distribution is much evil than before. Based on this idea, we can find this learning criteria or can enhance the discriminative power of the learned binary feature descriptor. For example, we want to emphasize this learning criteria is also is unsupervised learning techniques. This is also the key difference between our learning criteria with some the state-of-the-art deep learning model, because most state-of-the-art deep learning models learn features based on CNN or is supervised. So our method can be performed or can be installed with the unsupervised setting. So let's see our results compared with previously phase recognition performance. So this is the method. We conduct our experiments on the well-known RFW dataset. We know there are 6 different settings in RFW dataset. One is unsupervised, one is weakly supervised without the additional data, and some others like supervised setting with outside data, or supervised setting with outside large labeled data. So in this case, because we just no need the label information of the training sample, we just compare our method with 2 settings. One is unsupervised setting, another is weakly supervised setting. So we can find that our method achieved very competitive performance with state-of-the-art method. Or this is the previously method we can find. To further improve the performance of our method, we can do some engineering work, because we can sample the patch with different scales or different sizes. That to say, we can sample the patch with 3 by 3, 5 by 5, 7 by 7, 9 by 9. And then we combine these local feature vectors together to get a high dimensional feature representation. And then we combine this together to do the recognition. We can find that the performance can be further improved. For example, here we combine the 3 scales, and then we can find this performance is 82. Previously, if only 1 scale, the performance is about 89 or 87. So this is the first key idea of our local binary feature learning method. Is we want to learn a local descriptor which is compact, and we can make the bins. We can make the distribution of the bins as uniform as possible. This is the first idea. So after this work, we also improve the performance of our method. We want to address some issues in the CPFD. So let's come back to the LBP feature. We can find the LBP feature is a two-step procedure. So what's the meaning of two-step procedure? For example, we first give a patch. We can do the computation between we can compute the difference between these elements and the central elements. So we can get after that, we can do the Schwarzschild holding. We can get 0001 or something like this. And then we can do a feature encoding. We can get a number for this local patch. We consider this as a two-step procedure. First, for this part, to this part, we think we consider it as a mapping stage. Even there is no learning procedure or no learning steps in this procedure. We can find it because the Schwarzschild holding operation in this step is very simple. We just compute the difference between these elements together. So we consider the first part is feature learning, or feature, at least is feature mapping for view value to the binary code value. For this second part is we consider it as feature encoding. What's feature encoding? Here's the binary code. This is binary code. For this binary code, we can have many types of feature representation, not only this encoding approach. So what is LPP? LPP here is just a simple computational. Here is just a simple encoding. So in our CBFD, here we just learn a projection. This projection is learned based on 3 criteria, but we haven't do many things on this part. On this part, we just do the k-means. We use k-means to learn a dictionary to get the codebook and then to encode each binary code as a feature vector, histogram feature vector. So we want to improve this limitation. Why? Because this stage and this stage are performed individually. That's to say, some useful information may be powerful for feature encoding will be lost in this part. So what we want to emphasize, we want to make this stage and this stage to be conducted together. That's the reason why we proposed a method called simultaneous local binary feature learning and encoding. This paper is published in ICCV 2015. So what's the key idea of this approach? First, we also do the PDV feature vector. So based on this PDV feature vector, we not only learn a projection W, we also learn a dictionary D. This projection and this dictionary are learned together, are learned simultaneously based on this training set. And then given a test image, or we can get some patch, we can obtain the PDV value. And then we can make the PDV feature vector in a feature representation by the learned W and B simultaneous. The key idea is previously some useful information will not be lost in this stage because these 2 stages are learned jointly. So based on this idea, we can represent the same image where here is the patch as a histogram. So we can find our method compare with the previous method. These two steps of learning criteria can further improve performance. Here we missed one comparison because we also compare our method with CBFD in our paper, but we haven't listed here. We can find that these improvements sometimes maybe 1 to 2% improvements. That to say, a two-stage learning criteria is worse than a one-stage simultaneous learning stage or approach. So based on these 2 local binary feature learning, both of them are unsupervised. That to say, we haven't used the label information to do the local feature learning. Sometimes in some other computer vision applications, for example, age estimation. For age estimation, the key objective is we want to estimate the age value for a human face. So in this case, we can have the label information, and this label information is somehow different for human identity information. Because for human identity information, sometimes there is no ordinary relationship between this identity information. But for age estimation, the identity information of these training samples are usually ordinary and ranked. For example, 1 year old, 2 years old, 20 years old. This is ordinary. So what we want to emphasize is we want to explore this ordinary information. We want to explore this ordinary information to learn the binary feature representations. So for each face image, we also get some local patches, and then we can get a PDV value. So for this PDV value to project the local binary feature vector, we developed a cost-sensitive learning criteria. So the cost-sensitive learning criteria is we want to develop a different cost function to encode the loss. That to say, if we misclassified the image from or the face image with 20 years old to 25 years old, and the face image with 20 years old to 50 years old, the loss is different. So we went to using this cost function to infer this loss information. Then this part, cost function, is developed by human knowledge, or is developed by user, or is set by user. Then we can encode this function into the local binary feature learning part. And similarly, we can also have a codebook learning and some other part. And then we can encode this face image as a histogram image, or almost similar the same. The key difference is here. We use a cost function to highlight or to reflect the loss of different misestimation of age, of human face. So we can find how to achieve this. The key idea of this is here we have 3 local patch. So, for example, four local patch. Here is one patch. Here is one patch. Here is another 2 patch. We can find this 2 circles with the same age value. These 2 parts, maybe they are from different age groups, but the age difference is smaller. For this one, for this pair, they are also for different people or different age groups, but the pair but the difference is larger. So what we want to do is with our learned binary feature representation, we want to achieve some objective. First, the same age group, that to say face pair or image pair with the same age group, we are pushed as close as possible. And then, even if they are with a smaller age difference, the difference is smaller than the pair with larger difference. That to say, the order information of the pair is preserved. So here we investigate different types of cost function, but this cost function is developed by us. That to say, is not learned in the optimization function. So that to say, here CQ is predefined. So here we have 2 terms. One term is we want to achieve a large module learning criteria to make the learned binary local feature vector discriminative. The second one is we want to learn the binary feature descriptor cost sensitive. So based on this idea, we have a representation or feature representation for the whole face image, and then we do age estimation. Based on the learned feature representation. Then we can compare our method with the state-of-the-art age estimation method. We can find our performance. Our method achieve very, very competitive performance with state-of-the-art age prediction method. So there are 2 advantages for our method. One is our method can learn more discriminative our powerful local binary representation. Previously, you can find this one, or something like this one. Originally, this method used in some well-defined or handcrafted RAM features, but we can find our method can achieve better performance. So recently, we also explored the relationship of the binary code in our learned feature space. So previously, our CBFD method, we find the learned binary code is learned individually. What's the meaning? This 1, 0, 1, 0 for each bit is learned separately. For example, in the original LBP method, we have a criteria that to say the original LBP method sometimes called have a encoding pattern called the uniform pattern. What's the key idea of uniform pattern? That to say in the obtained binary stream space, we just only compute the occurrence for this binary code, which only have at most 2 times transitions. What's the meaning? For example, we have a 8-bit binary feature vector. One is 1, 0, 1, 0, 1, 0, 1, 0. Another is 1, 1, 1, 1, 0, 0, 0, 0. For these 2 types of binary code, what's our preference? We will prefer the second one. That was in the second one, the translation is usually much less than the previous one. So we want to explore this contextual information. Here, the contextual information means this we want to make the constraint of this binary code. That to say, the binary code is not only learned bit by bit. We want to learn them together. That to say, jointly. We want to make a constraint to consider the transition times between the learned binary code for 1 to 0. So here we have some, previously maybe CBFD is learned like this, but in our case, context-aware local binary feature learning is expected to get some binary code like this. So this is our idea. We can find this method can achieve much improvements, more improvements compared with the CBFD method. We can find the CBFD method with this, our setting is 88, but currently our method we can get 95. That to say, using more human knowledge or more prior knowledge to learn this binary feature or local binary feature can get more improvements. So conventional local binary feature descriptors usually is not rotation robust. For example, here is the texture image. For this texture image, sometimes there are some rotations between these images, especially the text classification. So in this case, previously the PDV value can compute based on a squared patch. So in this case, the PDV is not rotation invariance. How to achieve or how to make the learned binary representations can achieve the objective of rotation invariance? We can set an ordinary or a baseline. For example, in this case, we can set this direction as the ordinary PDV direction. For other case, if there are some rotations for these PDV vectors, we want to learn two parameters. One parameter is to project the PDV feature into the local binary feature. The second one is we also want to learn some theta. Theta is the rotation. That to say, we want to automatically learn the W projection and the rotation parameters together, which can make the learned binary feature descriptor not only discriminative but also rotation invariance. So in this case, we propose a method of learning rotation invariance local binary descriptor. So this method had been tested on face recognition with rotation, texture classification, and object recognition with rotation. We can find, especially for texture classification with rotation, this performance can achieve about 20% improvements because based on this learning criteria. Previously, the rotation variations was not considered. So this is some details. So we propose a term rotation binary patterns describe the rotation change of the sampled patch and the expected learned patch, and then we can find this will make the learned binary code more discriminative. We can find our method achieve the very, very powerful performance compared with the previous method. So not only for face recognition, binary feature representation can be also used for other visual recognition application. For example, we also make this learning based binary feature learning to image matching. For example, we want to describe an image patch with a local binary feature representation, but we also use unsupervised learning criteria. What's the key idea of this method? This method was published in EPFL last year. We called this method is learning compact binary descriptors with unsupervised deep neural network. Previously, the supervised deep neural network, like a CNN model, train a model. First, we feed one image into the network, and at the top layer of the network, we make some objective function. The objective function can use in some optimization criteria, especially like the softmax or some others, to learn the model and then to backpropagation for the model. But in this case, what's the difference? We have two differences. At the top layer of the network, we will not use the softmax. We use this learning criteria. We can find this learning criteria is almost the same as our CBFD criteria. CBFD criteria has 3 terms. We also use these 3 terms to set here. And the other part, the input is not only a holistic whole image. We just use a local patch. So this local patch feed into the network, and then we can do this. Based on this learning criteria, unsupervised learning criteria, we can back propagation the network, and then we can get the parameter of the network. For example, given a test image patch, we can feed it into the network, and then we can get a local binary representations. So for the image matching or the image recognition, we can compute the similarity between the local binary representation and the whole data sets. So the idea is very simple. We can find it also achieve very competitive performance. So another contribution of our work is we have another data augmentation criteria. In this paper, we also have another data augmentation because we want to make some previously data augmentation is just do some flipping or some rotation to make the training set larger. But in our case, we're using some prior knowledge to do the data augmentation. For example, if the image or if there is no rotation in the image, sometimes if we want to do the data augmentation, we want to do some rotation to augment the data set. We using the prior knowledge to do the data augmentation. For example, if two images have smaller rotation difference, the possibility of generate or synthesize this data is high than the two images with higher rotation difference. Based on this criteria, we can generate more models or more samples to train the network. This network or the pre-trained model of the network is using a VGG net. We can find our method. For example, we train the model on we train a model on one data set and test it on another data set. We compare our method with SIFT feature descriptor. SIFT is a view-valid feature representation, and our method achieve comparable performance. So this year we also have another CVPR paper because last year our deep binary representation also has one limitation. What's the limitation? In the top layer of the network is used a CBFD criteria. There is one significant or limitation in CBFD method or learning criteria is the quantization is just a binary. That to say, these types of quantization cannot handle the distribution, the sample distribution with a mixture Gaussian model. So in this paper, we publish we propose the method learning deep binary descriptor with multi-quantization. What's the key idea here? Let me see this. Previously, in the top layer of the binary feature learning criteria method, most using the sign function to get the binary representations. But this sign function usually ignores data distribution. For example, if there are two local patches which are very similar together, but if you using one sign function to do the shared holding, sometimes here is 0, here is 1. That to say the distribution of this patch is not considered. So what we want to do is we want to handle some complex distribution. One is we want to model the distribution of the local patch with a Gaussian mixture model. Then we can do the shared holding at different shared hold, and then we can make or get better binary code. So this paper will be presented the day after tomorrow. So in this work, we also proposed a method called K autoencoder. It's almost similar to K-means, which can cluster this local patch into many groups, and then we can do the clustering or shared holding for different groups. Then we can do train this model, and then we can retouch this KE for given training samples. So this part is almost the key part of this network. So previously, input is also an image patch, and then we can fit it into a convolutional neural network, and then at the top layer here is a fully connection network, and then here is just our multi-quantization network or multi-quantization loss part, and then this top layer is the output of our binary code. So this whole network is trained jointly. So we can find our method can achieve further improvements. Here is 27. Previously, last year, CPR is 29. The error rate can be reduced to 2%. The second application of binary feature is for visual search. Here, maybe we can't call local binary feature, but the key idea is almost the same. If we have a local patch, if we want to search the local patch for a large scale database, we also want to encode the local patch within a binary code, and then we can do the large scale search, large scale similarity search based on the learned binary code. So here we can do the image and the large scale image and video search. The key idea is we want to find the most similar image and videos among the dataset. So this learning or this method can be also used for different visual applications like the product search, medical search, and person VID. So previously in this large scale search, design of the hashing function is also very important for effective search. The key goal of this method is we want to get compact yet discriminative binary code. For example, here we have some datasets. For each dataset or for each image, we can get feature representations, and then we can get a hash table. For this hash table, we can encode this whole image as a local binary code. So in this query image, we can get using this hash code to encode it as a binary code, and then we can do the similarity search based on the Hamming distance. We can get the searching result. So in CPR 2015, we published a paper using called deep hashing for compact binary code learning. The key idea is we first compute the feature vector for each image among the dataset, and then we feed this feature into the deep network. But this deep network is different for the conventional CNN model, convolutional neural network. Here it's just a fully connection layer. So layer by layer is stacked. At the top layer of this network, we just we place a binarization part of the network. So here is the view value output. Here is the binary value output. We want to emphasize or want to achieve some objective or based on this binarization part. So here we also have three terms. One term is quantization loss, binary bits, and the independent bits. The total learning criteria of our method is also the unsupervised learning. That to say, in this case, the large scale similarity search can be performed with the unsupervised setting. That to say, the label information of the training set is not used in our learning criteria. So this is the learning criteria. We can find, besides these three criteria, we can also encode a discriminative part in the learning criteria. For example, we want to emphasize the similarity part of the samples from the same class is the similarity is as larger as possible, and the similarity of different samples, the binary code, the similarity of the binary code is as smaller as possible. In this case, we can employ a discriminative learning combined with this three learning criteria. Then we can find the binary code learning is very useful. So in this work, we developed two. Sorry. In this work, we developed two methods. One is called deep hashing, it's unsupervised. Another is called supervised deep hashing, it's supervised. So we compare our method, this DH with this unsupervised hashing method, and this SDH with the supervised hashing method. We can find that our method can compete most compared method. So after this conference version, we also extend our conference paper to a journal paper in this year. We published a paper in a TIP. So we extend this deep hashing for multi-label search. Multi-label search is the meaning of it. We want to consider the relationship of the samples with different labels. We want to compute the similarity of two images which have different number of labels. So we reformulate the between class and the within class of original SDH, which is proposed for single label hashing for the multi-label samples. then we can get. For multi-label scale, multi-label visual search, the evaluation criteria is different for the conventional single-label search, because the conventional single-label search, the MAP is usually applied. But in this case, we also use these two criteria. This year, we also have another work to enhance the learning or the Hessian learning method. Previously, I mentioned in the top layer, the quantization part usually has some large loss. So what we want to do is we want to emphasize this multi-quantization. This year, we improved this method, not only use the multi-quantization, we use a method called discrete hashing. So we propose a method called nonlinear discrete hashing. So first, we extract the features for each image, and then we feed it into the network. At the top layer of the network, we not only use a sine function to approximate the view value. So here we use a discrete hashing. Discrete hashing, that is to say, we learn the binary code bit by bit. In this case, the loss function can be well reduced. So we can find the NDH compared with our previously deep hashing. We can find that the MAP can be improved significantly. That to say, at the top layer of the network, the quantization loss is very, very important to get the compiled binary code. So besides on image search, we also applied our method to video search. In this year, we also have a paper published in this journal, deep video hashing. For the difference between image hashing and video hashing, so we want to consider the temporal information around the neighboring frames or within the video. So here we just consider, for example, if we perform an action in the video, what we want to emphasize is some neighboring frames which describe the same action. The binary code of this frame should be similar. So we have some first pass each frame into a deep network, and then we can compute the binary code, and then we can do the feature pooling among the neighboring frames. So at the top layer of the network, we also using a large margin criteria. Then here is also a sine function. We have many solutions to do the fusions among the network or among the videos. Then we have early fusion, late fusion, and slow fusion. We investigate different types of fusions to check the performance of this video hashing performance. I think we can get for each video clip, we can get some neighboring frames. We can get a video binary code for a shot, and then we can get many binary codes. And then within this binary code, we can do some pooling. We can get a binary code for the whole video. Here is the performance. We can find this is the latest deep video hashing, because compared with the image hashing, video hashing is less investigated. Besides the deep model, we also consider the structure information of the samples within the frame. For example, if we have a video, this video can be contain maybe 1,000 frames. For these 1,000 frames, some frames occurred in the same or in a similar scenario. That to say, some frames can be grouped together. So we first do the subspace clustering within the for the frames within the same video. So we can get many subspace. What we want to do is we want to cluster this subspace together, and then we encode the binary code for this subspace, and then we can get many binary set for this subspace. So another video maybe is short, maybe 1,000 frames or 100 frames. So we can get another number of binaries as a binary feature set. So we can compute the two sets of binary feature matrix, which select the most similarity. So in this case, we can consider here is a set, here is another set. This set is described by several subspace, which subspace is described by binary feature vectors. So we can compute the most similar pairs of these two videos. We can do the video search based on these two most similar subspace. So here is the key performance of our proposed method. So last is the summary of our local binary feature method or local binary feature learning method. We find the learning local binary feature is very effective for many visual applications, not only for visual recognition, visual search. We also use it for image matching or object detection in our ongoing project. More efforts are desirable to further improve its view application, especially in structured Hashi and unsupervised Hashi. That to say, unsupervised binary feature learning and structured supervised binary feature learning, we can pay more attention for these two directions. Last one is new criteria are also required to better evaluate the performance of different Hashi methods. For example, previously just using MAP. MAP criteria is similar to the recognition rate, but sometimes in this case, the difference between visual search and visual recognition is not highlighted. In visual search, usually the setting is somehow different for visual recognition. So new criteria, we can better describe the difference between visual search and visual recognition. Not only MAP should be preserved. Last, we need to, this work is collaborated with some professors, like Professor Zhou Jie and Dr. Zhi Xiang and Duan Yueqi and Wang Zimei from Tsinghua University. I also have some collaborators in Singapore because I worked in Singapore for 8 years before I joined Tsinghua. Here is one of my interns, which also help us to do some binary feature learning. He also published a paper in CVPR last year. That's all. Thank you. Sure.
My concern is about the robust of the binary features against the affine transform or noise, such as so on. So I want to about this.
In terms of noise or in terms of variations like rotation or noise, for my understanding, local binary feature sometimes has some advantage compared with field value. Why? For example, let's give an example. For face recognition or face representation, give a local patch if there are some variations on the lighting or illumination. So if we do the local binary feature representation, the effect of this illumination can be well addressed in this local binary quantization part. But rotation, if we don't expectedly address the rotation, both real valued feature and binary feature are not so powerful. Deep learning is powerful.